Good morning. My name is Ogbodo Nkiruka from Alex Ekweme Federal University, Ndufu-Alike, Ikwo in Ebonyi State of Nigeria. Today I'll be making a presentation on behalf of my research team on the topic Chemical Kinetic Study of Consecutive Irreversible Second Order Methanolysis of Sea Almond Seed Oil, SASO. This research paper presents the kinetic study of alkali-homogeneous irreversible second-order methanolysis of seed oil derived from sea almond. For this presentation, I will be talking on the following outlines: introduction, background study, objective of the research, methodology, results, and conclusion. The tremendous challenges on the environment due to the application of fossil fuels have made the application of alkyl esters derived from natural sources relevant. This has led to the production of biodiesel in a large scale by methanolysis of seed oils, considering the fact that the physicochemical characteristics and energy attributes of biodiesel are similar to that of petrodiesel. According to Reyero et al. 2015, the homogeneous base catalyzed transesterification using methanol, resulting in the production of fatty acid methyl esters, FAMEs, is actually the predominant technique applied for large-scale production of biodiesel. For this research, application of methanol was necessitated because it's readily available and cheap. The use of homogeneous base catalysts like sodium hydroxide and potassium hydroxide at commercial level is highly encouraged because of their catalytic activity compared to acid catalysts, which are more corrosive. Although many researchers have investigated the reaction kinetics of various vegetable oils, this particular research investigated the kinetics of methyl ester production from non-conventional, non-edible tropical seed oil of sea almond, which before now was treated as a waste after consuming its juicy pulp. For the successful scale-up of laboratory results, information obtained through kinetics and optimization studies are necessary, hence the need for the chemical kinetic study of this process. Algae in 2012, Danako and Cyril in 2000 proposed that methanolysis reaction constitutes 3 consecutive irreversible steps by using high methanol to oil molar ratios in the production of biodiesel. The high molar ratio of the methanol shifts the reaction mostly to the right, thereby making it an irreversible process. Objective of the study. This research proposes the kinetics of biodiesel production from sea almond seed oil on the basis of irreversible consecutive mechanism. The materials used in this research include sodium hydroxide, methanol, carbon tetrachloride, which is solution, potassium iodide solution, and phenolphthalein. They were all of analytical grades. The seed oil used in this work was extracted by solvent extraction method, and the fruit seed biomass were gathered from Onitsha City in Anambra State of Nigeria. The physicochemical characterization of the seed oil and the biodiesel have been conducted and reported previously by Esonye et al. 2017. Also, the rate of reaction and its mechanism as regards to the transesterification process of the seed oil were investigated by considering irreversible conditions. From literature, the kinetic studies of transesterification reaction includes 3 consecutive irreversible reactions, yielding fatty acid diglycerides and monoglycerides as intermediates. The following equation represents the summary of the reaction stages. As proposed by Elgin 2012, Danako and Cyril 2000, The experimental data were processed using the following irreversible assumptions. Firstly, a perfectly stirred batch reaction is considered. Secondly, the methanolysis reaction is constituted by 3 consecutive stages, but assumed irreversible because of the excessive presence of methanol in the reaction. Thirdly, the catalytically active species is sodium methoxide, formed by a reaction of sodium hydroxide with methanol, which is a fast reversible reaction. The experiment was designed to determine the reaction rate constant using the ratio of 6:1 for methanol to seed oil. To examine the temperature dependency of the reaction rate constant, the reaction was studied at the following temperatures: 55 degrees centigrade, 60 degrees centigrade, and 65 degrees centigrade, using 0.2 weight% of sodium hydroxide as the catalyst at atmospheric pressure. The amount of triglycerides, diglycerides, monoglycerides, total methyl esters, and glycerol content in the biodiesel batch production were determined, with diglycerides and monoglycerides having minimal quantity of less than 3%, while triglyceride was 94%. This shows the processes involved in determining the quantity of triglycerides, diglycerides, and monoglycerides present in the biodiesel production. Furthermore, to test an already developed kinetic model for an irreversible second-order reaction based on triglycerides hydrolysis by Dianaco and Cyril 2000. A model was developed as stated in equation 5 below. Rearranging and resolving the equation gives equation 6, where K is the overall rate constant, T is the reaction time, Tg0 is the initial triglyceride concentration. Also, a plot of reaction time T against 1 over the concentration of triglycerides will give a straight line if the model is valid. Finally, the activation energies of the reaction taking place were estimated using the calculated rate constants and temperatures at which they were observed in Arrhenius equation stated below, where EA is activation energy, R is the gas constant, A is Arrhenius constant or frequency factor. From the observed data, diglycerides and monoglyceride relationship with time followed the same trend with that of triglycerides. Results and discussions. Table 1 shows the physicochemical analysis of the Sea Almond seed oil and its biodiesel compared with international standards. The properties analyzed include the density, flash point, kinematic viscosity, iodine value, cetane number, moisture content, pore point, cloud point, saponification value, refractive index, and calorific value. The obtained values were compared with the American standards ASTM 6751 and ASTM 9751. Also, the European specification DIN 14214 was used in the analysis. ASTM 9751 is for petrodiesel standards, while ASTM 6751 is for biodiesel standards. From the results obtained, the percentage conversion of triglycerides recorded for the seed oil ranged from 89% to 91%, compared to 91% obtained by Kuma et al. 2011 and 98% obtained by Dianaco and Cyril 2000 after 1 hour. Figure B, I to BIII shows the progress of the intermediates at 55 degrees centigrade, 60 degrees centigrade, and 65 degrees centigrade, respectively. While figure C shows the effect of the reaction temperature on the transesterification reaction for sea almond seed oil methyl esters. Table 2 shows the summary of kinetic results for second-order irreversible reactions of sea almond seed oil methyl esters. From the results obtained, it is observed that K increased with increase in temperature. The activation energies of the reaction were estimated using the calculated rate constants and temperatures as stated in Arrhenius equation. Although the kinetics of the base catalyzed transesterification of sea almond seed oil is not yet documented in literature, the values of the activation energies obtained for sea almond seed oil methyl ester is similar to 14.7 and 14.2 kilocalories per minute obtained for triglyceride and diglyceride hydrolysis of palm oil, as reported by Danako and Cyril 2000 at the same temperatures. The value of rate constant for triglyceride hydrolysis obtained in this research is about a factor of 4 higher than that determined by Danako and Cyril 2000 for palm oil at the same conditions, and a factor of 2 lower than the values reported by Rero et al. 2015 on the kinetics of sodium hydroxide catalyzed transesterification of sunflower with ethanol. This shows that the process is, however, faster and advantageous when compared to the previous works. The higher activation energy of 22.43 obtained for the monoglyceride hydrolysis clearly shows that higher temperatures favor the reaction step more than other steps with lower activation. Also, the positive value of the activation energy supports the endothermic nature of transesterification process, according to Rero et al. 2015. The proposed model, figures A, B, C, shows the second-order reaction irreversible model of triglycerides, diglycerides, and monoglycerides hydrolysis. The figures represent the plot of reaction time T against 1 over the concentration of triglycerides, diglycerides, and monoglycerides, which gave a straight line with hard values of coefficient R squared. From these plots, it can be confirmed that the model is valid. Also, the model predicts that maximum monoglyceride yield decreases as the reaction increases. This could be due to the fact that the conversion of monoglycerides into glycerol has the highest activation energy among the 3 transesterification steps. The results also shows that the kinetic constant of the first step, which is the hydrolysis of triglycerides into diglycerides and biodiesel, has the smallest value, and it's therefore the slowest and the rate determining step. Summary. The research predicted a valid kinetic model for sodium hydroxide-based catalyzed methanolysis of sea almond seed oils, which describes the effect of temperature on the oil conversion and yields of biodiesel and the intermediate triglycerides and monoglycerides on irreversible basis. It was observed that the seed oil conversion increases with increase in temperature, with complete conversion achieved at about 40 minutes into the reaction. Also, the rate constant of sea almond seed oil methyl esters methanolysis showed that monoglycerides hydrolysis has the highest value, with obvious increase in the rate constant with increase in temperature. Finally, the results confirmed that the hydrolysis of triglycerides to diglycerides was the rate determining step for the irreversible reaction conditions. Those are the references used in this presentation. Thank you for listening.